So today's science seminar is about ocean heat uptake in the changing climate. Ocean heat content actually is a critical element of the Earth's energy budget, and Saurabh's been working on this as part of his PhD for the last year or so. And what you're about to hear actually is basically a conference presentation he gave at the Australian Meteorological and Oceanographic Society 2 weeks ago, and represents some of the work out of the first year of his PhD project. We anticipate it will go for about 25 minutes. That will leave us 10 or 15 minutes to ask a few questions and perhaps pick up on some of the key messages. So without further ado, we'll let Saurabh take over. What he'll do is share the screen, which will be a PowerPoint presentation, and you'll hear Saurabh as we progress. So over to you, Saurabh.
Thank you, Nathan, for the introduction. And the title of my talk is Hemispheric Asymmetry of Upper Ocean Heat Content and the Role of Natural Variability. Someone's microphone.
It's all right, just keep talking.
This is the outline of my talk. We do have some background study and motivation for our work, and we do have some result analysis of the ocean heat content in our field.
Is there someone there with the if you could mute your microphone, that would be great. Thank you very much.
Thank you.
So continue on, sorry.
So this is the outline of my work. We do have some background study and motivation for our work, and there are some results showing the analysis of the ocean heat content in Argo period 2005 to 15, with different products and the factor contributing to this change. And in the end, we do have some conclusion and summary of our work. So we know that the ocean contributing a lot to our daily weather activity and the long-term climate system as well. And whatever the heat which is stored in the Earth system since 1970 is getting deposited into the ocean, and the amount of that heat is around 94%, and the rest 6% is getting deposited into the different part of the climate system. We can show the atmosphere, continent, glacier, sea ice, and the Antarctic of sea ice of the Arctic and Antarctic. This is the annual time series of the global ocean heat content for the upper 700 meter since 1950, and we can see that after 1970 there's a rise of ocean heat content, and we can see that in the last decade from 2000 onwards till 2011 and 12, the rise of the heat content is quite high, and it is increasing in a very rapid manner. So that this period was known as the hiatus in the global warming, in which that most of the heat is getting deposited into the deeper depths of the ocean. When this hiatus occurs, so the reason of this hiatus is suggested by England et al. 2014. It is one of the mechanisms which is showing that due to the strengthening of the trade wind, there was a persistent La Nina condition on the equatorial Pacific Ocean. So this kind of phenomena of the equatorial Pacific is absorbing the heat from the atmosphere, and this heat is getting deposited into the deeper depths of the Pacific and get transported to the Western Pacific. After that, this heat has been transported from the Pacific Ocean to the Indian Ocean through ITF, and this study has been done by Lee et al. 2015, which is showing that there is a rise of the global ocean heat content, and although the global ocean heat content was rising, there is a drop of the ocean heat content of the Pacific Ocean. But at the same time, the Indian Ocean was getting the pace in the ocean heat content heat uptake. So based on this study, there are some motivation for our work. Is we have to examine the hemispheric asymmetry of the global ocean heat content, which is present in the upper 2000 meter for the period of 2005 to 15. And we also want to assess the contribution by the different ocean basin towards this observed hemispheric asymmetry, and the possible role of the natural variabilities, which are involved in this kind of the distribution of the global ocean heat content across the hemispheres. So for this purpose, we use the data. We do have some observation data, that is the SCIP Argo product, IPRC Argo product, and the Hatley products. Then we do have some reanalysis product, the ORAS and SODA. Then there is a wind product from the Airline trim, and there are the different climatic indices. This is the Nino 3.4 index and Southern Annular mode, Indian Ocean dipole mode, Pacific decadal oscillation, and Atlantic multi-decadal oscillation. And these are the results. So in the result, this is the first result, which is showing the monthly time series of globally integrated ocean heat content, which is starting from 2005 to 2015. And we can see that the black curve is the global ocean heat content, which is the ensemble mean of all the oceanic reanalysis and the observation product. So this global ocean heat content is continuously rising from 2005 to 15, which is closely followed by the southern hemispheric heat content, which is shown by the red curve. But surprisingly, we can see that the northern hemisphere is showing a very strong hemispheric asymmetry, and it is showing a cooling trend. So we can see that there is a there is a very strong hemispheric asymmetry between the southern hemisphere and the northern hemisphere, which is present in the upper 700 meter. Whereas if you see in the 700 to 2000 meter, this asymmetry, the asymmetry is still present, but it is not as strong as it is present in upper 700 meter. And then the southern hemisphere is still at a bigger hand. But the gap between the southern hemisphere and the northern hemisphere is not as wide as it is present in the upper 700 meter. Now we want to see that how different ocean basins are contributing toward this hemispheric asymmetry. So the upper panel is for the upper 700 meter heat content, and the lower panel is for the 700 to 2000 meter heat content. So in the upper panel, we can see that the Indian Ocean is the largest contributor, followed by the Pacific Ocean and the Atlantic Ocean. Whereas in the 700 to 2000 meter, all the ocean basins are showing the rising trend, in which the Atlantic Ocean is the largest contributor, which is followed by the Pacific Ocean and then Indian Ocean. The interesting thing to note from this analysis is that there is the ensemble, the curve which is shown in the black line, and all the other products are shown as a spread across the ensemble mean. So we can see that all the products are agreed very well between this period. So this ensemble mean is showing us a very robust analysis that there is a very good signature of the ocean heat content, the ocean heat uptake in each and every ocean basin. And other than that, we can see that before 2010, when the hiatus was there, when the hiatus was present at the time, so the Indian Ocean was rapidly rising in the heat before 2010, and after that it was having some kind of flatness. But if you see in the Pacific Ocean, so we can see that the Pacific Ocean was reducing the heat uptake before 2010, but after 2010, the Pacific Ocean is again started gaining the heat. So there is some kind of the ocean heat content redistribution present between the Indian Ocean and the Pacific Ocean, and this kind of redistribution is just because of the presence of the hiatus, which is showing some kind of Indo-Pacific ocean heat content redistribution. After that, these are the linear trends and the role of the surface winds which are present, which is showing that how this heat is getting deposited in the different ocean basins. So we can see that the large part of the global ocean heat is at 40 degrees south, and which is contributed mainly from the Indian Ocean around 40 degrees south and the Pacific Ocean around 40 degrees south. And there's a strong cooling pocket which is present in the equatorial global ocean and in the high latitude of the global ocean. So these cooling pockets are contributed from the Pacific Ocean in the upper tropics and the Atlantic Ocean at the high latitude. These kind of the convergence and divergence of heat is getting arise due to the dynamics of the wind. So we can see that around 50 to 40 degrees south, there is a strong anticyclonic wind circle present. Because of this, the heat content is getting deposited into the global ocean around 40 degrees south, and after that there is a strong convergence which is presented in the upper tropic, which is getting highlighted in the Pacific Ocean. And the similar the cyclonic wind circle is present in the high latitude of the Atlantic Ocean. In the spatial pattern, that is the lowermost panel, we can see that the most of the heat is getting deposited into the Indo-Pacific basin around 40 degrees south latitude band. And here we can see that this is the most heat is getting deposited into the Indo-Pacific Ocean around 40 degrees south, and after that there is a signature of ENSO is also present in this thing. In the upper 700 meter, we can see that there is a wide contrast between the southern hemisphere and the northern hemisphere, in which the equatorial, the upper tropical Pacific and the North Atlantic is showing a very robust cooling, and whereas in the southern hemisphere around 40 degrees south, the Indo-Pacific basin is showing a very strong warming. So this is a thing which leads to the hemispheric asymmetry of the global ocean heat content. And the other important thing to note is in the high latitude of the Atlantic Ocean, in which the upper 700 meter is showing a very strong significant cooling trend, but in the 700 to 2000 meter it is showing a very strong significant warming trend. So there is some kind of vertical dipole structure which is present in the Atlantic, and we still want to investigate that why this kind of phenomena is present in the North Atlantic, and why this cooling is not propagating down to the deeper depth, or vice versa, that why this warming is not coming on the surface from the deeper depths of Atlantic Ocean. Now to estimate the role of the natural variability in this redistribution of the global ocean heat uptake, where we use two type of approaches. The first is like the simple linear regression, which is shown in this equation. This is similar to y equal to mx plus c, and the second method, we use the multilinear regression analysis, in which we want to see that what is the role of the different natural variabilities, that is ENSO, IOD, SAM, PDO, AMO, etc., which can affect the redistribution of the global ocean heat uptake. So in this analysis, we use two kind of ENSO indices. So NINO1 is the conventional NINO 3.4 index, but the NINO2 is the Hilbert transform of NINO 3.4 index to accommodate all the fair share of ENSO index from 0 to 360 degree, and this NINO2 index is something like which can give you the non-linear coupling between the ocean and atmosphere as well. And then the one thing that I want to point it out, this delta T. So delta T is the time index, which is shown here as whatever the time index minus the middle of the time series. So that is the delta T. So we are interested in the regression coefficient B from the simple linear regression analysis, and this B1 from the multilinear regression analysis. So this B1 will give us the true underlying trend which is present from the global warming in the ocean heat uptake. After that, I want to give a note on this, that how we use this kind of indices is like these nano indices and the IoT index and the SAM index. We just make them the high frequency indices. That is the intra-annual indices. And the PDO and AMO, they are the low frequency indices which will accommodate the decadal to multi-decadal variability. The main challenge of this analysis is like we are having a very shorter ocean record, that is just the 11-year ocean record. But so if we want to look into the decadal to multi-decadal kind of analysis within this period, so that is little bit difficult. And from our analysis, where we came to know that the Atlantic multi-decadal oscillation doesn't have any severe effect if we eliminate it, or if we account it in our analysis. It won't create any kind of problem, because it can't be accommodated within this shorter ocean record. So the major player for the shorter ocean record is the ENSO and the PDO. So they are having a very profound impact on the analysis of on the analysis of global ocean heat content. And the other thing is the IoT index, which is a very region specific thing. So if we integrate the effect of IoT across the globe, then it is not as much as strong as ENSO is, because it is very region specific thing. And the separation of this high frequency and the low frequency indices has been done by Zhang and Church 2012, and Francom et al 2014. So they just clearly mentioned that how to separate the high frequency and the low frequency to make them far apart, and make them independent from the influence of each other. So from this analysis, this is a simple linear regression of the ocean heat content. So we can see that all the variability means all the variabilities are present into this kind of linear regression analysis. And what is the need for doing the multilinear regression is like on a very shorter ocean record, which is starting from 2005 and ending at 2015. So 2015 was a case of super El Nino. So which is giving some kind of aliasing effect on the trend calculation within the shorter ocean record. So we want to eliminate this kind of aliasing effect which is present, which is arising due to this kind of the extreme natural variability occurrence. So for this purpose, we use the multilinear regression analysis to remove all the components of the natural variability, and just to get the true underlying trend, which is a representative of the global warming signal. So this panel B is a reconstruction from the multilinear regression analysis, and we can see that with the help of all the indices and all the partial regression coefficient, we are successfully able to reconstruct the ocean heat content time series, and we can see that both the patterns are matching exactly with each other. So the panel A is from the simple linear regression analysis, and the panel B is a reconstructed ocean heat content trend from the multilinear regression analysis. So after that, this panel C will show you that there is a coefficient B1 which is related to the time trend. So panel C is the partial regression coefficient B1, which is just related to the time trend from the multilinear regression analysis. So we can see that we are successfully able to eliminate the El Nino signal, which is presented in the simple linear regression analysis, and which is also giving the aliasing effect of the trend calculation over the shorter ocean record. And by the use of multilinear regression analysis, we are successfully able to eliminate this kind of natural variability. So if we see that what are the natural variability present were present into the shorter ocean record, so we just take a difference from the we just take the difference of simple linear regression analysis and the multilinear regression analysis. So we can see that there is a strong influence of ENSO which is present across the equator, there is a very strong signal of IPO or PDO, which is also present into this analysis, and there is a very slight influence of IOD as well present into the Indian Ocean. So this kind of natural variability we are successfully able to eliminate by the use of multilinear regression analysis from the ocean heat content, and this kind of technique was well established technique and was successfully implemented on the surface variable like SST or the precipitation or the sea level. But this is the first time that we use this kind of technique for the ocean heat content analysis. So after that, we want to look into the latitudinal contribution of the global ocean, the latitudinal contribution in the global ocean heat uptake in the depths of 0 to 700 meter and 700 to 2000 meters. So for this purpose, we use normalized cumulative sum. So normalized cumulative sum is given by the cumulative sum which is from the southern hemisphere to the northern hemisphere within the Argo domain, which is from 62 degrees south to 62 degree north, and it is the zonally integrated regression coefficient, that is B and B1, which is normalized by the total heat accumulated at 62 degree north, and which is zonally integrated by the multilinear regression analysis, that is B1. So by the use of this normalized cumulative sum, we will get to know that how the heat is distributed across the globe at each and every latitude, and what was the difference between the simple linear regression analysis and the multilinear regression analysis after and before eliminating the natural variabilities such as ENSO and PDO and etc. So this is the raw trend that I already shown, which is from the simple linear regression analysis, and we can see that there is a strong dominance of ENSO, which is presented in the upper 700 meter spatial pattern along the equatorial Pacific. So this kind of signal is giving some kind of aliasing effect within the shorter ocean record. So after using the multilinear regression analysis, where we can see that this thick continuous line is from the multilinear regression analysis, and all the dashed lines are from the simple linear regression analysis. So by looking into that, we can see that most of the global ocean heat is getting stored into 30 to 50 degrees south. That almost 100% of global ocean heat is getting dumped around 30 to 50 degrees south, in which if we won't eliminate this kind of natural variability which is arising from ENSO or PDO, so the southern hemisphere is getting underestimated, and the northern hemisphere is getting overestimated, which means that the southern hemisphere is actually absorbing more heat, which is suggested by the simple linear regression analysis, and then the northern hemisphere is losing less heat, which is suggested by the simple linear regression analysis. So we can see that the presence of the natural variability will distribute the global ocean heat uptake across the hemisphere, and if you won't eliminate this kind of natural variability, so the true underlying trend is getting aliased. So, and this is the example that we can see that how the southern hemisphere is getting underestimated and how the northern hemisphere is getting overestimated. So in the upper 700 meter, the Indian Ocean is the largest contributor toward this ocean heat uptake, and it is contributed almost 100%. So whatever the extra heat that is stepped into the Indian Ocean is getting is compensated by the Pacific Ocean. We can see that in the upper tropical Pacific Ocean, there is a huge reduction of the heat uptake, and also in the Atlantic Ocean. So before eliminating the natural variabilities, we can see that the Pacific Ocean was showing around 30% of heat uptake, but after eliminating the natural variability, the Pacific Ocean is dropped down to 5 to 7% only. And the Atlantic Ocean is showing more cooling, as it was showing before eliminating the natural variability. But the interesting thing to note in the 700 to 2000 meter, in which there is not much changes across the ocean basins, and all the ocean basins are behaving in the same way before and after eliminating the natural variability. So this analysis shows that the deep ocean heat uptake detection is quite robust, and it is less affected by the presence of natural variabilities. And the lower panel are showing the zonal cross sections of the ocean heat uptake after eliminating the natural variability. So we can see that there is a huge intensification across the Indian Ocean at 40 degrees south, and in the Pacific are around 30 to 40 degrees south. And in the spatial pattern we can see that there is a huge intensification in the mode water region in the Indo-Pacific basin after eliminating the natural variability, and there are some other changes in the Atlantic Ocean. So in this way we can see that the large deposition of the ocean heat uptake after eliminating the natural variability is presented into the Indo-Pacific subtropical gyres, and these because of these reasons there is a robust and a strong hemispheric asymmetry present in the upper 700 meter of the ocean heat uptake. And if you see in the last panel, and if you compare the panel H on the left hand side to the panel H on the right hand side, there is not much difference in both these panels, and both these panels are looking exactly same. So we suggest that the deep ocean heat uptake is the detection of the deep ocean heat uptake is quite robust in the 700 to 2000 meter depth, and it is less affected by the presence of natural variabilities. So these are the conclusions from this talk. There is a presence of a strong hemispheric asymmetry in the upper 700 meters compared to 700 to 2000 meter, and almost all the heat is taken up by the Indian Ocean, and this rise of heat in Indian Ocean is getting compensated by the reduction of heat uptake in the Pacific Ocean and the Atlantic Ocean, and then the tropical Pacific and the North Atlantic cooling is responsible for the low heat uptake of the northern hemisphere. So because of the cooling in the Indo-Pacific subtropical gyres, because of the warming of the Indo-Pacific subtropical gyres and the cooling in the North Atlantic and then the tropical Pacific, giving rise to the hemispheric asymmetry for the upper 700 meter, and this hemispheric asymmetry is very strong in upper 700 meter as compared to 700 to 2000 meter, which is suggesting there is a strong influence from the presence of natural variabilities on the upper ocean heat uptake. Now we want to further investigate that whether this asymmetry is from the natural decadal variability or due to the cooling effect of the anthropogenic aerosol in the northern hemisphere, and whether this asymmetry will persist in the near future as well, or it is just the transient effect because of some kind of hiatus effect or due to some other things. And the key message from this analysis is failure to remove the natural variability from the ocean heat time series lead to underestimation of the southern hemisphere heat uptake and the overestimation of the northern hemisphere heat uptake in the upper 700 meter. And the detection of the deep ocean heat uptake is quite robust and is less affected by the presence of natural variabilities. Thank you.
Thank you very much, Saurabh. You might just stop sharing so we can actually see the questions. Thank you very much, Saurabh. We've got a few questions in the Zoom chat group, so maybe we just scroll up to the top and we will start. Saurabh.
These are the questions.
Yep, so I guess that's a question from Dom32, from Katya. What is the standard pattern for the spatial linear trend from ensemble mean slide? So you just might click back and then
So Katya, this was the pattern means before eliminating the natural variability. So This is in the upper 700 meter, and this is from 700 to 2000 meter. So these are presence of strong heat uptake in the subtropical gas.
This is the mean. I was wondering about the standard deviation.
Sorry, the standard deviation. So the spread of this pattern.
Yeah. So we haven't got it here.
We haven't got it to show you. So.
But you can analyze. But you can see that that almost all the products are getting closer to the ensemble mean. So I think the spread of the standard deviation is will be quite less.
Yeah. Yes. In the basin it looks in the basin average it looks very similar. But I wonder if they had any local spread.
Yeah.
Atlantic or in the Indian Ocean.
Yeah, so we haven't had it here, but I will do the analysis and I'll send it to you.
So we did. So Katja, we did do a cross comparison of all the products, and some products are less satisfactory, if I can put it that way, and some are pretty consistent. And there were some anomalies in some of the products.
Yeah, so we are getting some kind of outliers in like Orus. So you can get some kind of the outfit of Orus product, and mostly in the Atlantic and in the Pacific.
Yeah, my suggestion was just to, when you show the ensemble mean for the regional patterns, you maybe add a slide for the standard deviation, so you can have an idea of what is the spread at the grid points.
Yep, sure.
So on some of the figures, Katja, you'll have seen there's 6 individual lines in grey, and
those. I mean for the basin average. I mean for the
It's spatial patterns. Yeah.
All right. Yes. So thank you, Katja. So we'll go to the next question, Saurabh. So from Afrina, I think it is, to everyone, what is the NAO index for linear regression? So you see the question there, Saurabh?
Yeah, I think. What about the NAO index for linear regression gives the change in the North Atlantic? So Katya, we had done this analysis, and we came to know that the effect of this AMO pattern is very small on this kind of shorter ocean record, and then the magnitude of this the magnitude of that variation is quite small. So whether you want to keep it or whether you want to eliminate it, it won't affect the analysis drastically.
But the now is different from AMO, isn't it? The now in that.
I think
the now moves more quickly than the AMO.
Oh, okay, but we haven't took this index into our consideration. So I was just looking for the decadal to multi-decadal variability, and there was a paper from Robson in 2016, which is showing that there is some kind of trend reversal in the North Atlantic. Previously, it was having a very warming trend, and now it is having a very robust cooling patch over the North Atlantic. So by following that paper, I just considered to take the AMO index rather than the NAO index. Yeah.
Okay, so let's go to Afrina, which I think is the next question actually.
So the natural availabilities, Afrina, they are like the El Nino or La Nina, means commonly known as ENSO, then IOD, Indian Ocean Dipole, Southern Annular Mode, and Pacific Decadal Oscillation and Atlantic Multi-Decadal Oscillation. So these are the natural variability that we were referring to, and we do have the equation for that. So I'm going to share that equation with you. So this is the equation in which you can see that these are the ENSO indices, and this is the Indian Ocean Dipole mode, this is the Southern Annular mode, then this is Pacific Decadal Oscillation, and these are the Atlantic Multi-Decadal Oscillation. So all these are the natural variabilities, and this B1, which is the partial regression coefficient of time, this will give you the true underlying trend, which is just attributed towards the global warming, and it is free from all these natural variabilities. So I hope that I am able to answer your question.
You're welcome to talk, Afrina.
Yep, sure. And is the heat in a specific deep ocean currents or in the whole deep ocean body? So,
so we're now answering the question
policy
from Nick Woods, actually, at the beginning.
Yeah. So, Nick, means for your question, we are having this analysis. So you can see that for 700 to 2000 meter, all the ocean basins are showing a uniform warming pattern. Means that there is not a very strong warming or the cooling patch present in the 700 to 2000 meter, except in the North Atlantic Ocean. So there is some kind of vertical dipole structure present in the North Atlantic, which is showing the upper 700 meter as a robust, significant cooling patch, and there is a robust, significant warming patch in the 700 to 2000 meter. But other than that, all the ocean basins are showing uniform warming pattern. And you can see from the time series analysis as well, for the 700 to 2000 meter, all the ocean basins are continuously rising in heat, and there are not other fluctuations present into this 700 to 2000 meter, which is showing that the deep ocean heat uptake is quite robust, and we can attribute it to something, but yet we have to investigate it in more detail.
So maybe, Nick, the surprise here really is that there are very strong natural fluctuations, the El Nino for example, the El Nino in the upper 700 meters, but at deeper depths, actually, the signal is much, much more robust, and the sort of variability, if you like, the ocean noise is much weaker.
Yeah.
And you can really see that in those bottom three panels in this figure.
Yeah, it's very impressive, and when you sort of look at the fact that there's these big deep ocean currents, but that is so uniform that is genuinely alarming. It's so strong. Yeah.
It is, and the curious thing is that and I think earlier you made a comment, is the North Atlantic cooling? It is cooling over the last 10 years. Yep. And we don't have a clear explanation to that. The upper 700 meters is sort of slops around, driven by winds mainly, and that's the source of much of that variation you see in the left panel there.
Yeah, and if you will follow the paper from Robson 2016, so they mentioned that this kind of cooling is from the melting of ice from the Labrador Sea, and which is making it like a less dense water, and which is situated over the top of the 700 to 2000 meter. But it is still surprising that why this cooling is not extending down, or the vice versa, that why this heat is not coming up to the surface. So we still don't know about that.
Okay, so maybe thanks, Nick. So Nick, maybe go to the next question there, Saurabh. So we've
what is the
Afrina says thank you, thank you, Afrina. And then back to Katja, I think here. Yeah, so you can.
So actually, we do have a slide for that. I think back in my slide.
Because it seems that the warming around Australia in the southeastern Indian Ocean and Western Pacific, rather than probably the full Indian Ocean. Maybe the North Indian Ocean contribution is more compared to those two sectors.
Yeah. Actually, we do have a slide of your interest.
Just click back. You actually have it. Oh, I see. Going there. All right. You can also see it in the cumulative plots, Sora.
Yeah. So that the cumulative plot will also give you some kind of idea about that. What is the percentage of the Northern Indian Ocean and the Southern Indian Ocean? But here also you can see that the Northern Indian Ocean is like 0.64, but the Southern Indian Ocean is like, you can add it for the upper 700 meter. So that is a very large
uptake. 30 to 20 north, capture is probably 70% of what the Southern Ocean is doing.
Yeah.
0.7.
And then you can look to the community plot as well. If you like, then I can show you again.
So it's mostly on the southern section, in the Southern Ocean. If you look at the Indian Ocean, the Pacific.
Yeah, well, mostly at the mode water location, you will get the most of the heat is getting deposited around 40 degrees south, both in the Indian Ocean and the Pacific.
It's not clear yet if it's heat uptake or changes in the distribution, maybe.
Actually, means people were talking about this intensification of sand, so there will be more churning of the gyres wave. So the churning of gyres wave will increase and the heat is getting deposited. But we need further investigation for that whether it is coming from the innovation through flows pathways or whether it is just getting deposited due to the churning of gyres.
There are more than one.
So back to the questions, Saurabh, so that whether there are any more questions from people. Have we covered everyone's questions in the chat channel? Are there any more questions?
I just have a comment. So we have a new map for...
Katja, let's just see if there's anyone else who wants to ask a question.
I think we're done with the questions. Yeah.
All right. Okay, back to you, Katja. Apologies for that.
Yep.
We have a figure that is going to the state of climate bands, and they're showing the change between 2017 and 16. So now the North Atlantic, where you have the cooling, has changed. It's warming now compared to...
Yeah. So actually, I think Katja, we should consider this comment. But due to the limitation of 1 hour of the ORUS, which is just till 2015, so we just restricted our analysis to 2015. But I think it is good to look into the present scenario where what is going to happen in the North Atlantic as well.
Yeah, it's just to say it is changing again.
Yeah, sure. It's a good feedback. Thank you for that.
Okay, so thank you, Katja. If there aren't any more questions, let's just thank Saurabh for his presentation today, and let us finish off the web today. And if anyone wants to stay behind, we can have a conversation, but otherwise we can end the presentation from the Earth System Science Climate Change Hub. There will be further presentations progressively over the year. I think I'm down to talk about the special report in the oceans and cryosphere I've forgotten when, but it's coming. Thanks very much, everybody.
Thank you, everyone.
Thank you.